Okay, today we're going to talk about the process capability ratio, and it's a way of determining whether or not your current operation meets the specifications, or it can be done within the specifications. And in fact, a good way to see this, if this will page down, maybe best way to think of this is to look at maybe something like this. So suppose you have a target here and you have a machine, it's set to hit the target. And so the one machine hits the target like on the left here, and the other one hits the target like on the right. And you can see this one has some in the center. Let's say you're trying to get in this weight circle here. This one's kind of all over the place, but it has a few in the center. And this one here has none in the center. And the question is, which is easier to fix? Of course, this one here is so random that there's really not much you can do. But over here, you can kind of re-aim the gun or whatever you have firing, and you could get it to where if you moved it here, you could hit the target real easy. This one, it's just so random, no matter what you do, there'd be no way of adjusting this. So when we talk about these process capability ratios, that's kind of what we have in mind, is that, let me go back here. Ideally, we would like something like this. So you have your dimensions, you're supposed to make a part between this dimension and this dimension, and your control limits are falling within here. So that means the vast majority of your parts are going to be well within the specification. So this is something good, obviously. This is what we want. What's bad, of course, is if it's the other way around. If these are our dimensions we're trying to make our part according to, but our upper control limit, lower control limit are outside these, then we're going to have like a lot of bad parts out here. And so obviously this is going to be a bad situation. And we can calculate what's called this process capability ratio. Again, you'll actually do the calculations, so I won't go through them here. And what happens is it will tell you like how much of your process could be put within the acceptable range. It doesn't necessarily tell you that it's in this acceptable range right now, but the higher that value is, if it's greater than 1, at least you can maybe move your mean to where you can get all your parts made within specifications. If this CP value is less than 1, then you're going to have a lot of unacceptable parts. So again, up here with what we had before, the upper and lower control limits are well within our specifications. Here, they're not good. Again, in this case, the CP value will be lower when things are not good. And again, the one problem with this calculation is it only compares the width of the tolerance limits with the width of the control limits. It doesn't say that the mean of your process is in the center. And so, like I said, so like you could actually have something like this. Notice the width of your control limits are nice and narrow, but they're much narrower than your specification limits. So in this case, the CP value will be high, which indicates it's good, but unfortunately, since your mean is so far off, it's still going to have a lot of bad parts. So this is again is the case where, you know, like the target we had like all the shots in one spot, which is good, but our mean is off. But still, a lot of people use this to calculate the capability of their operation. And so again, like I said, in this case here, like say, maybe in this case here, your CP value would look real bad because there's no chance of fixing this. In this case here, your CP value looks good because even though you're off the target, you can kind of adjust your shot to get within your target like this. And now there are other types of calculations you can do that will take into account not only how wide your control limits are compared to your specification limits, but also kind of tell you how close you are in making parts correctly. And I have another handout I'll give you here. And this kind of gives you a lot more detail. And so let me pull this up and let's go through this a little bit. And so, yeah, let's take a look at this. Let me share my screen in the right spot. So yeah, so on this handout again, this first page shows you the process capability ratio. And again, if things are exactly aligned, so your upper and lower control limits are right in line with your upper and lower specification limits, in that case, it'll be 1. And let me make this a little bit bigger. And again, obviously, if you're outside the limits, then things are these are going to be bad parts. But again, this would be kind of the average good position. Your CP value is exactly 1. Things are exactly lined up. And now in this case here, again, in this case, the upper and lower control limits are way outside, so there's going to be a lot of bad parts because again, here's your specification limits in here. And again, in this case, in the case I just showed you, the CP value would be real low. And again, now in this case here, it's going to be real high because here, so in this case, the CP value is shown to be, if I can adjust this, it's going to be probably much greater than 1 because here's your upper and lower control limits going to be like here, and yet your specification limits are way out here, so you only have a small number of bad parts, and that'll give you again a high CP value. Again, the higher the better. But as I mentioned before, the only problem is the CP value doesn't tell you how centered your process is. It only tells you how wide your control limits are. And so, so you need sort of more information than just to have the CP value. Now, the one thing though is if your CP value is below 1, again, it's just not possible to adjust your process to get within the control limits. At least if it's greater than or equal to 1, even if it's misaligned, you can make an adjustment to get it within the specifications. Now, there's another calculation, what's called the CPK, as it says here. This will actually tell you how much of your process actually falls within specification limits. it doesn't only take into account the width of your upper and lower control limits, but also takes into account how centered everything is. So in this case, if the CPK value is greater than or equal to 1, then you have six sigma limits fall within the tolerances. If it's less than 1, then they don't fall within the tolerance limits. The other thing that you can get from this is, now again, if you do have the case that's the CPK is less than 1, and it's between, say, 0 and 1, then the process mean is within the specification limits. If it's equal to 0, then the process mean is equal to one of the upper or lower specification limits. If it's between -1 and 0, the process mean is completely outside the specification limits. And if it's less than -1, then the whole process is outside the specification limits. And so there's some other things that you can find out. If it happens to be that the CPK calculation, CP calculations are exactly the same, then your process is centered. If the CPK is less than CP, then the process is not centered. Again, you'll when you do problems, you'll kind of see all this. You don't really have to understand it right now. And then there's yet another calculation. It's called the CPM. Again, CPK gives good indication how much the interval is inside the specification limits, how much outside. And this one gives an indication of the centering of the mean to the middle of the tolerance limits. And there's a bunch of calculations here. I won't go through them because you'll actually do some problems related to these. And here's some pictures that kind of give you an idea what's going on here. This one would be the ideal case. You have high CP value and high CPK value. Again, it's well within the upper and lower specification limit. This is roughly, it's almost saying it's like twice as narrow as the upper and lower specification limit. It doesn't come out exactly that way, but that would kind of give you a general idea. So if those are both above 1, that's really the ideal case. In this case here, again, you notice this is much narrower than the actual design tolerances. And so things are still good. This again is much narrower. That's why this is 2. It's much narrower than your upper and lower specification limits. And this kind of indicates it's still well within the tolerances, even though it's not centered, because it's above 1, that you're still going to be making most of the parts within your control limits. And in this case here, it's kind of just on the edge. Once again, see, notice this doesn't change because the width of this is always the same compared to the upper and lower specification limits, all the last 3 cases. So that's always 2, because that's only telling you how wide this is compared to the dimensions you need. And now this is kind of telling you that you're still within the tolerances, but you're kind of maybe right on the edge of one end or the other. And now here, see, once again, this is still 2, again, because this is so much narrower than what your dimensions are. But this, because that's below 1, it's telling you you have a lot of bad parts because your process is actually outside the limits. A lot of bad parts are being made over on that end that are bigger than they're supposed to be. And again, this case here, if CPK is 0, that means that your mean is actually right equal to one of the either upper limit or the lower limits. And so, you know, if your part's supposed to be between 1.9 and 2.1, it's saying your mean is at 2.1, which means all these parts are bad. But once again, notice your CP, that still looks good once again, because it's narrow, and also because if you could adjust your process, you could get it well within tolerances. And again, this case here, CPK is outside. And so the mean is actually even outside the limit, so that's why it's going negative here. And -1 for the CPK indicates the whole process is outside the tolerances. And here's one final example here. And notice this case here, the mean is well centered. But again, you can see the upper and lower control limits are outside or wider than the specification limits. So in this case, it's 0.8. So no matter how you adjusted this, you couldn't improve this. Again, because this is equal to this, that indicates the process mean is right at the mean of the upper and lower specification limits. And then finally, if you have a case like this, again, we have the same width as the last picture, but this time our mean is all the way to one of the extremes of the dimensions. So, yes, you can take a look at that. Again, we'll do some problems related to this now, kind of help you understand these. And let me see. And so let's start probably let's start with this one. So you can go ahead and start working on this again. You can kind of read back and forth between the handout to get an idea what all this stuff means. Again, I probably have repeated some of these ideas a few times, but again, that's the first couple of pages of what we talked about, and that's also in your handout. So let me go back to here. Yeah, take a look at yeah, so you can take your time, read through the stuff, then start looking, like say, at some of these problems. Look at number 1. Again, maybe make a sketch of this to get an idea. Oh, yeah. Oh, the other thing I forgot to mention is on one of your equation sheets, let me bring that up here. And one of your equation sheets, can't remember which one it was. Probably confidence interval. No, it's not that one. Oh, probably control. I bet the control chart one. Let's see. Yeah, let me see. Probably on equation sheet control charts. Yeah, if you have the one that says, yeah, if you have the one that's called equation sheet control charts. Yeah, if you have this one here, equation sheet control charts, and the equations that we're looking at are on like the 3rd page. of that equation sheet control charts. And again, let me zoom this a little bit. So if you want CP, it's this equation right here. CP, upper specification limits, lower specification limits. And so take a minute, think about that, then maybe I'll sketch some out here. This is the mean. Do this here. So the mean and standard deviation are 2.3 and 0.5. Again, you might want to make a little, take a minute to think about what a little sketch of that would look like. Let me just get a ruler here, otherwise it'll be a mess. So again, the mean is 0.2. Again, maybe you want to make a little sketch here. So 0.15. Yeah. And again, we want to put plus or minus 3 sigma. Turn it this way a little bit. So if we go, say, plus 3 sigma, again, this would be 2.45, 260, 2.75. If I'm doing that correctly. And then the other way, again, 1, 2, we need one more, don't we? Now let's see, looks like that's going to be minus 1.85. So this is be 2 point, excuse me, that's not right. 2.15. Let's see, 1, 2, actually, that I put this in the wrong spot. 2 and minus 1.85. So again, if we go plus or minus 3 sigma, it would be something like this. So if I can draw this neatly, which I probably can't, it'll probably look sort of something, like this. And then here's our 3 sigma limits here. And our specification limits are 1.9 and 2.6. So that's going to be maybe about right here. Let's say the lower specification limit. And the upper specification limits up here. And again, you can see that, let's see, so anything down here are going to be bad parts. Anything up here going to be bad parts like this. So that's kind of what the sketch would look like. And then go ahead and use that equation, go ahead and calculate what that would be. And let me go, that's the wrong picture. And use this here. Yes, sir.
Is there any way of knowing that the chart will go outside of upper and lower limits before calculating CP?
Let's see, about what you can say is, yeah, if you do, let me think of it, yeah. Yes, you could probably say that this difference, so like this difference, this is, the CP is this divided by, this 1.85 is 2.75. That's basically, so this would be the 6 sigma limit. And then visually, probably not. Well, yeah, I guess you could. Yeah, that's right. I guess if this, right, I guess if this difference was bigger than this difference, then I would be telling you the CP is going to be less than 1. But if this difference is, oh, wait, I said the wrong way, didn't I? If this difference is bigger than this difference, then CP will be greater than 1. And the other way around, if this difference is smaller than this difference, CP will be less. Yep. Yes, in this case here, then we would have CP like we have on our short. There's U, that's L, that's S, L. And so divided by your 6 sigma. And so in this case,
Is there a reason why 1.85 is negative?
because I made a mistake. Sorry. Yeah, thanks. I was thinking I was subtracting on the other end, and I had a negative in my mind. Yeah, so please make that positive. Thank you. Yeah, please fix that. So yeah, that's should look something like that. And then, so then our upper specification limits are 2.6 minus 1.9. And then 6 sigma is 0.15. And that's going to be 0.7 divided by 6 times 0.15.
let's see. No, I did something wrong. Yeah, 0.7. Yeah, good. Yeah, that's right. Yeah, so this is, so what do we get? 0.77 for the first one? Yeah, so yeah, another thing, like Ethan was asking, the other way to think of it is if this width here, this, let me adjust this a little bit. So if you were to measure this, the USL length, this is like what, about 2.25, maybe a little bit more. That's 2.25. And then our Six Sigma limits, if you measure those, are about 3. So the fact that the specification limits measure like, say, 2.25, which is smaller than our Six Sigma limits, so to speak, our upper and lower control limits, the fact that the USL minus LSL is smaller than the upper and lower control limit indicates CP is going to be less than 1. That's one way to think of that.
I think the upper, is 4.7, not 4.75.
Oh, both. Yeah, thank you. Oh, yeah, thank you very much. Yeah, please fix that. 4.7. Again, the CP value looks good, but there are a lot of bad parts. Actually, pretty much everything, everything here is going to be bad. And they're, for the most part, everything within our Six Sigma limits. Interestingly, a few that are way outside our limits will be good. But again, the idea is the CP value kind of just tells you the width of your process compared to the width of the upper specification limit. So in some ways, it does give you a lot of indication. Like we said before, you may be able to just adjust your process and then get things well within your tolerances. But on the next part there, that's one of the weaknesses. So the weakness is that it may not tell you CP, may not give a good indication of your current process. It only tells you and again, it may indicate how good your process is if if the mean is centered, but it just indicates. It does indicate though that your process mean could be changed so that you could put things within tolerances. So yeah, that's just sort of a start. So go ahead and continue the next page will have it calculated. And like I say, for the next one, use that other equation.
Wants to draw the full sketch again.
You don't have to. No, you can. Yeah, right. For actually 2A and B, you don't have to draw it again. And same with 3A and B. I believe they're all the same. Yeah, you don't have to draw it. I don't know why I said that. Just do the calculation, and you can kind of refer to the picture you already drew. And then, like I say, when you do these other calculations, there's a CPK. And then for problem 3, the CPM. Yeah, so for this case here, for the CPK, and actually what I'll do, I'll just calculate those two separately. So like the equation sheet said, let me write that down. So CPK is equal to the minimum of USL minus the mean divided by 3 sigma, and mu minus the lower specification limits divided by 3 sigma. And we want the minimum of these two. And so it's going to be the minimum, in our case, let me be sure I do this right. Upper specification limit is 2.6. Let's see, almost 2.3 divided by 0.15. And then in this case, let's see. Yeah, in this case, this will be 2.3 minus the lower specification limit 1.9 divided by 3 sigma. And that'd be 2.6 minus 2.3 divided by 3 times 0.15, 0.67. And this would be 2.3 minus 1.9 divided by 3 times 0.15. 0.88. So it looks like the minimum of those two is 0.67. And then the next case. In the upper specification limit, 4.7 minus 4.9. Am I messing this up again? No, upper specification, yeah. And then 3.05. And the mean 4.9. Lower specification limit 4.3. 5. Divided by 3 times 0.05 minus 1.33. We'll at the minimum of those two. 33. See if that all makes sense. By the way, my sixes and sigmas look a lot the same. And so this. So let's say we have this one here. And so for 1A, is the mean centered in the middle specification? Then we can actually will need the CPK for that. And as it mentions over here, that has to be equal I'm looking at the wrong one. If we look at this process handout here, and so if CPK is equal to CP, then the process is in the center of the specification limits. And if CPK is less than CP, then it's not at the center. And actually, it would have to be equal. So in this case, we would say, of course, it's no, it's not in the center. If the answer is no, is the mean equal inside or outside? And so, again, because it's between 0 and 1, the process mean is inside specification limits. So this would be inside. And then are the 6 sigma limits currently within side the process? And then we have here CPK is less than 1. The answer is no, huh? So let's see, if CPK is less than 1, then the 6 sigma limits do not fall within the tolerance limits like this. In that case, if the answer was no, go to 4. So suppose the mean could be moved. Is it possible for this to and the answer is yes. And we should let me put some reason down here. Yes, again, because CP is greater than or equal to 1. And this here was no, because CPK was in this case less than 1. And number 2 here is the mean equal to inside, and because CPK is between 0 and 1, then it's inside. And then of course for number 1, this is specifically asking whether it's centered in the middle. That's just a specific question. And again, the reason it's no is because CP is not equal to CPK. And so then we can look at some of our graphs to do the last part. We kind of go through these and say, okay, we know it's not centered. So we know it's not that one. And it's not that one because it's centered. And also it's not this one because it looks like, well, I'll save that for the next one. So let's look at the next one here. Now, possibly this, oh, thank you. Hold on. I knew I left them somewhere. Thank you. So this one here, let's see, possibly this or this possibly could be a candidate, huh? Let's see. Does it look like if we move these, we could get these within the specification limits? I'm thinking it looks like it could be 3. Let's look at the next one. See, it's probably not 4 because 4 indicates CP is going to be greater than or less than 1. In our case, CP was greater than 1. So this would be a CP that's greater than 1 because this is so wide. So it's probably not 4. So far I'm thinking 3 would be the answer. And it's not this one because it noticed that the mean is right on one of the upper or lower specification limits. And that would be if CP is 0, so it's not that. And it's not over here either because it's the mean is not outside the specification limits, because that would be the case where CP would be negative. So it's not that. Same thing for 7, CP would have to be negative. 8, CP, or excuse me, CPK, I should have said would have been negative. Here again, CPK would be 1, and also those are wide. Again, it's probably going to be figure 3. These are so far outside. Yeah, it looks like figure 3 would be the case. See, it wouldn't be figure 11 because CPK is less than 1, whereas in figure 11, the whole process is within the specification limits. And in that case, CPK would have to be greater than 1. So yeah, it looks like figure 3 would be the best candidate. You have the case where your CP value looks like it's bigger than 1, because if you could move this here, this could be within your specification limits. And yet CPK was between 0 and 1, which indicated the process mean was within the limits. So that's kind of like what you would go through to try to figure out where things are falling, if that makes sense. Is the right answer.